Hello guys, welcome back to the channel EC TechNest. In the 100 Days of Digital Design in Verilog series, today we're going to speak about an important concept that is counters. A counter is a sequential digital circuit that counts the number of clocks or events. We have two types, one is asynchronous counter and the other is synchronous counter. So what happens in an asynchronous counter, the clock pulse is connected to the first flip-flop and the output of the first flip-flop is again given as input clock to the next flip-flop. There is no common universal clock for all flip-flops. Only the first flip-flop is driven by the main clock and the others are driven by the outputs of the previous flip-flop, causing the count to ripple through the circuit. Rippling is nothing but it is passing from one flip-flop to the another flip-flop. Now we have synchronous counter. I'll explain in detail how to do this and all, but let's just know what is counter for as of now. Asynchronous counter is where the clock pulse, whatever is connected, is common to all the flip-flop. It means it is driving all the flip-flops simultaneously. Here, the main advantage is it can work at a very higher frequency because it does not suffer from delay. Now, you might ask, what is the problem with this? Why does this create delay? Because here the clock has to drive this flip-flop first, then drive this. So by the time it passes to the last flip-flop, it is creating a delay. So this is why we try to use synchronous counters in our daily to daily uses. Hence it is also called as parallel counter. Parallel counter because it is giving the clock pulse at simultaneous to the all the flip-flops, right? So parallelly it is working. That's why it's called a parallel counter. Here also it is given C. So all the output changes in parallel. It means when you are giving any input, all the four flip-flops will be updated in the same clock cycle. Ripple counters asynchronous. Okay. A ripple counter is called asynchronous because the clock signal is not connected to all the flip-flops simultaneously. Instead, the output of one flip-flop acts as the input to the clock input to the next flip-flop. For this, you can take the example of dominoes, where you just push the first domino and it moves and it makes all the other domino fall. So it creates a tripling effect. But it introduces a delay. Not all the domino will fall together. One by one, they'll fall. Here, the circuitry is very simple and it requires less power, but it is only suitable for low speed applications. If you are working around with a very high speed application, it can lead to glitches. So this is the Verilog code for our ripple counter. Here I have used a JK flip-flop. You already have learned how JK flip-flop works. So I'll just explain in brief. In a 0 0 condition, you get whatever is your previous state as output. 0 1, the circuit is reset. That means the flip-flop is in reset condition. 1 0, it is set, and in the 1 1 condition, toggles. Now what I'll do is I require four flip-flop, right? So I'll call each of them. I instantiate each of them into my ripple counter. The output will be the count will be of 4 bit, and my output Q bar, that is your final output, is of 4 bit is what I'm telling. Let us see what we have done. I have called JK flip flop for the first instantiation, and yeah, the main thing to note here is the J and K input is tied to 1B1. That is means to enable the toggle mode. If I give both J and K as 1 1, it will enable this toggle mode. I'll explain why we require this toggle mode in the next slide. Just remember this. So each J and K is tied to 1-B1 to enable the toggle mode. Then clock is connected to the clock, reset is reset, Q is connected to the count, then Q bar is connected to Q bar. So count is this. Here we connect the count one. Okay. So the first thing we do here again it is the same one. But you see here for the second clock, count 0 is the input instead of Q. Means I have connected the first input Q as count, right? So this is getting connected to the clock. Reset will remain the same. Here your output becomes count 1. This count 1 will become input for the next clock. So this is how you write your four JK flip-flops. So it can be used as a ripple counter, 4-bit ripple counter. Your final output will be count 3 and Q bar 3. That is here. Here you will get that count 3 and Q bar 3. Yeah, now we'll talk about why we need the J and K. Imagine that we are doing a mod 8 counter, or just consider as of now that we are counting from 0 to 7. So 0 in binary is 000, 001 for 1, 2 becomes 010, 3 is 011. Now that you might observe that the last bit, what is happening? Not much change. It is going from 0 to 1 and 1 to 0. Every single time a clock pulse arrives, the least significant bit LSB must change state. That means it will go from 0 to 1 and 1 to 0. By hardwiring J and K to logic 1, we force the flip-flop into that final row of truth table. Every time it sees a clock edge, it simply looks at its current output and flips it. Here we have 000. If this is the last bit is flipped, we get 1. Here again, this will increment, but again the last will get flipped. Same thing happens till you reach 111, that is 7. Hmm. After this, we'll understand what is propagation delay, because when we're talking about asynchronous ripple counter, this is the main thing that gets spoken. The total time it takes to the last bit to come out, this will be n into TPD. TPD is your propagation delay. In a ripple counter, each flip-flop has a small internal delay between receiving a clock pulse and updating its output Q. What we are trying to say is, once you give the input to the flip-flop, it will take a certain amount of time to update the output Q. Here what happens is, for the second flip-flop to work, it has to wait for the output of the first, and the third waits for second. So the delay gets added up, and it is very prone to glitches. When counting from 011 to 100, the bits don't change all at once. For a split second, the counter might show 010 or 000. Means what happens is, now you have given the clock pulse, but it is still getting updated. It's on the way to getting updated. At that time itself, it may take it as output due to the speed. Before settling, it will become this. So in high speed, if you're working on high frequency systems, it can cause incorrect middle value, causing a system error. We also have frequency limitations. As I told you here, this is not for high speed applications. Whatever asynchronous counter we are using, it is not for high speed application. So we have frequency limitations. The maximum frequency at which a ripple counter can reliably operate is limited by the total delay. To ensure that the counter settles before the next clock pulse arrives, the period must be greater than the total delay. So Fmax, what is your maximum frequency, should be less than or equal to 1 by n into your propagation delay. So what we are trying to tell is, here you saw for a 4-bit. If you are moving from a 4-bit to 16-bit counter, the circuit speed will drop significantly. Why? Because your propagation delay is increasing. More the number of flip-flops in asynchronous mode, more will be your propagation delay. Why we use T flip-flop versus JK? Most ripple counters are built using T flip-flop or toggle flip-flop. Here what happens is, we need to tie J and K to logic high. Positive edge triggered. If the FF flip-flops trigger on the rising edge and you clock to the next edge with Q, it acts as a down counter. Negative edge triggering. If the flip-flop triggered on the falling edge, what they mean to say here is, when you write your code, if you're using positive edge triggered, you will get as a down counter. If you are working on a negative edge trigger, that is falling edge triggered, it will act like a up counter. Simple. So you might ask, if there are so many problems with asynchronous counter, why are we using it? So the main reason why we are using it, it's an excellent frequency divider. The first output of the first flip-flop is exactly f by 2. The second will be f by 4. So the nth bit will be f by 2 power n. Why? Because of propagation delay. If you only care about the final frequency and not the exact timing alignment of the bits, a ripple counter is the most power efficient way to downscale a signal. That means you're reducing its frequency. Now we have synchronous counter. In a synchronous counter, the clock signal is connected to every flip-flop simultaneously, as we discussed in the second slide. How it works: to ensure the bits flip correctly without waiting for a ripple, we use combinational logic AND gates to determine if a flip-flop should toggle based on the state of all previous state. Here the thing is, it is extremely fast and reliable. Since everything happens at the same clock pulse, you do not require there is no delay. More complex wiring and logic gets as bit width increases. Let us see why we have complex wiring. So this is your 4-bit synchronous up counter, and this is your 4-bit synchronous down counter. Not much of a difference, but I'll try to explain both. What we will try to do is, we'll use the same circuitry, but we'll try to do both using single circuit. Rather than doing a separate up counter than doing a separate down counter, we'll do up down counter. So most of you will be knowing a T flip-flop, right? Now we are going for a synchronous up-down counter. Means up and down can be done at single time just by changing the control signal. The circuitry will remain same like this itself, but here an extra control signal will come. Rather than just a AND gate working and giving the output here, we'll have a mux. Let us see how we can do this using a mux. Before going to that part, let us see this how it works. So yeah, main thing is you need an excitation table of a T. First, you should be knowing the truth table. After knowing the truth table, you need to know the excitation table. So you have the two inputs, that is not inputs exactly. This is the present state and this is the next state. So we have 0011 and 0101. For that, what should be your input T? So we have written for to get 0 as the next input, our T flip-flop has to be 0. 0 1 it has to be 1, and 1 0 it has to be 1, and for 1 1 it has to be 0. Same way you will write it for 3 bits, because we are doing a 3-bit up down counter. You will write Q3 Q2 Q1 Q3 bar Q2 1 Q1 bar, present state, next state. Based on this excitation table, you will write the same for all the 3 bits. So 0 0 0 0 0 1. So if it is 0 0, you will write 0 0 0 0. If it is 0 1, it will become 1. Then for 0 0 1, 0 and 0 0, 0 and 1 it is 1, 1 and 0 1. So you see this table and write this excitation table. Now what will happen is you will get the values of T3, T2 and T1. Now that you have got it, you have to write the K map. So you have, this is for T3. So you should be knowing how to write a K map in order to design the up down counter. Once let us see for one example. We'll see for the this column, that is T3. Now we have 0001, 0001, 1000, 1000. So what you have to do it, we write the first key map. You put your all 4 inputs, that is your control signal M, Q3, Q2, Q1. So we have Q2 and Q1 here, and M and Q3 here. So this is Q2 bar, Q1 bar, Q2 bar, Q1, Q2, Q1, Q2, Q1 bar. Here you have M M bar Q3 bar, M bar Q3, MQ3, and MQ3 bar. So, writing a K-map, you have to know that you have to write the numbering like this: 0, 1, 3, 2, 4, 5, 7, 6. Then you come to the fourth row, you write 8, 9, 11, and 10, 12, 13, 15, 14. Now you can go back to your output of this T3. So 0, 1, 3, and 2. That is how your order goes, right? So 0, 0, 0, and 1. Because in the third position you have. Similarly, for seventh position you get 1. I again write it like this. So after filling in all the 16 bits, I'll get like this. 1, 1 here and 1, 1. So now I have to mark out the common terms. Here I have 1, 1. Here I have 1, 1. If you guys do not know flip-flop, please put it in the comment section. No, if you do not know how to write a K-map or work on a K-map, put it in the comment section. I'll make a separate video for this on K-map. Or else we'll do a thing for day 19. We'll completely keep it for like understanding how to solve a K-map. As of now, understand like this. We are pointing out the common terms. Here you have Q2, Q1, and here it is common to M bar Q3 bar, M bar Q3. So here Q3 and Q1 bar Q3 bar will become 1. So we are left with M bar Q2 Q1. This M bar Q2 Q1. Here again the same thing happens. We have M here. Q3 and Q3 bar becomes 1. We have M Q2 bar Q1 bar. That is how we get our T3. In a similar way, what we will try to do is we'll try to solve T2 and T1. T1, since we have all the words as 1, your T1 value will be 1. No need to write a gamma, but just have return it. Here again, you will write the same way. Here what happens is you will get 4 ones. We call it quad. Here what happens is Q2 bar Q1 and Q2 bar, you have Q2 Q1. So Q2 bar Q2 bar, Q2 bar and Q2 will go. We left with Q1. And here we left with M bar. So it becomes M bar Q1. Similar way, here again you get a quad and you get MQ1 bar. So this after getting the values of T3, T2 and T1, now you can write it down in the form of circuitry. Here you have your control signal M and this one, NOT gate. So you can have both zeros and ones. Yeah, here I can see M0 is count up, M equals 1 is count down. So I design that. Then I see what is required for T. First I'll begin with T1. T1 is, it requires 1. So I give logic 1 to T1. Then I get Q1 and Q1 bar as output rate. Based on my Boolean expression here, I require an AND gate and an OR gate. I've done the same here. No, I'm doing it for T2, right? M bar Q1 and MQ1 bar. So I connect it to M bar Q1 and MQ1 bar, and I connect it together to an OR gate, and it is given as the input to T2. Similar way we'll do it for T3. T3 requires more number of inputs, right? But since already have M bar Q1 here and I have MQ1 bar here, I just need to take the output from the previous one. We have taken here output from the previous one and given it as input. So this is how we design a 3-bit up-down counter. Similarly, you can do a 4-bit. My suggestion would be, since you already have two AND gates and an OR gate, you can write it in the form of mux. And yeah, how to count? So if you have n bits, so if you have 3 bits, 2 power 3 minus 1, that is 7. 2 power 4 is 16, minus 1, 15. So we call it mod 8 counter, mod 16 counter. So let us see a comparison. Clocking. Here what happens in ripple counter, only the first flip flop is clocked by an external source. Synchronous counter, all flip-flops are clocked simultaneously. Here it is slow, here it is fast. Ripple counter here is simple, but here it requires a lot number of logic. See, we have to do all this work to just design this one counter. But the better part is it can do both up and down counting. Here it is very prone to glitches. Here it is minimal, very less. If you have any doubts, feel free to put it down in the comment section. In the next video, we'll discuss on solving K-maps.